guessing this is pretty much where we left off last time, correct?
Yes, sir. Yeah.
So we'll continue the conversation from here, of course. And what other topics have been covered in this week?
Sir, we started. We're done with inductive effect. We have to do resonance now. Like we completed the first 5.
You started off with the effects basically. Inductive effect is completed, and
Yes, sir.
electromeric effect is also completed.
Yeah, hyperconjugation is also completed. Yeah.
Hyperconjugation is completed,
Yes, sir. Well,
but resonance is not done.
I mean, we're yet to do resonance. I mean, we started
The
masonry
picture is a
completely.
little weird, man. Seriously, this is not the first time I'm noticing this. This is not the ideal flow I would prefer any day. You'll understand when we are discussing hyperconjugation why I do not like this flow at all. So you do not understand what resonance is properly yet. Is that what I am supposed to assume? Or have you guys done resonance sometime long time back or something of that sort?
We've done resonance to an extent.
But you've not done resonance in organic, right? You have done resonance, if I remember correctly, from chemical bonding. The
Sir, we've
carbon.
done resonance in organic chemistry as well. Like, I mean, that's what we're doing right now. Like,
We've already done resonance in organic chemistry. Discussed
yeah,
resonance first,
yes,
and
yes,
then
yes.
only went into hyperconjugation then.
Yeah, like pretty much. Like he taught simultaneously, kind of.
Then that's what I was confused about. When you said hyperconjugation was completed, but resonance was not completed, it didn't make sense. Usually they need to be discussed in synchronization, usually. Otherwise,
Yeah,
it
that's
won't
what we did. Yeah.
make sense.
Yeah.
Then cool, my mistake then. I didn't get the full data as to what has happened. All right, so continue on. What else? Currently, you guys have covered hyperconjugation basics, and you are covering mesomeric effect in what to say? I'm assuming plus or minus R as of now. Is that correct?
R, no, we didn't do R.
Okay, all right, cool. And
So,
yes.
also, like a while back, you asked me why does resonance happen? Like, why does it tend to go to a lesser stable state and then come back?
So yeah, I did tell you, think, discuss, try to find an answer, and stop looking in chemistry, if I remember correctly.
Yeah, yes, sir. You're like, how come like waking up in the morning and stretching feels good, even though it's uncomfortable like that? Something along
Correct.
those
Yes,
lines.
it is.
Yeah.
It is. That is a very apt metaphor here. For instance, quartering used to be a punishment.
What?
Quartering means
No.
basically they hang you up like this by each extremity, and then they pull you
Oh.
up till you separate. Eventually, I think you get the terminology now as to
Yes.
where it
Yeah.
comes from. But
Yes, sir.
what to say? The idea there is, imagine if you're in that kind of a stretch position for like a few seconds. It feels fantastic, and then you come back. Right? That's when it feels fantastic. And just thinking about it makes me feel like stressing out. Stretch a little bit fully, and then come back. Now, so what is it that we gain? What is happening? Is that stretched position good for us? Is that a more stable state?
No, not more stable.
Right? It is an unstable state.
Yeah.
Correct. So, what is happening? What is happening here? That is an unstable state.
Yeah.
This is a more stable state. But
Yes.
going there and coming back makes this feel better. So, what's happened? In a sense, it's basically proving that the grass is not greener on the other side. Right?
Yeah.
In a sense, it is pretty much that only. But what exactly is happening here? You can look at everything from this point of view here. Now, everything which we have discussed over here is making sense logically, but it doesn't make sense mathematically.
Yeah.
So think mathematically, think physics now. What exactly is happening? We can't understand it in our state over here. That is a lot more complicated.
Hmm.
The metaphor here is for you to feel the effects of it, because it is pretty much a very apt metaphor to consider over here. But it is not the most ideal thing to look at it from the energy perspective there. So for the energy perspective, go to pure resonance chemistry there and try
Hmm.
to explain it using physics. Because understand that this is pretty much exactly what's happened over there.
Hmm.
Why is it that that is going to be superior? You're discussing aromaticity now, I presume. Is that correct?
Yes, sir. Yeah.
So now is the time when you should start exploring this question. So don't what do you say worry about it. The question is a little bit deep question. It is not something which is a small question. And when you're really looking at it from a physics perspective for the answer will be deep as well. And it won't connect one piece or two pieces. It will connect everything basically. It's physics.
Hmm.
Physics will not be just one thing. Physics will talk about effectively discussing. It will give you a different angle of looking at electronic effects completely. So let your electronic effects finish. By that time, if you have an answer for me, we will see. Because
Hmm.
what I'm trying to tell you here is the explanation for this logic over here will connect not just resonance alone, it will connect every possibility, meaning it will connect your hyperconjugation, it will connect your aromaticity, everything will get connected together. Because if the understanding is crystal, it's as simple as that. Things basically like everything connects. So now you have to look for a physics explanation of resonance. The question is the same. The question remains the same. I just want you to look at a physics explanation. And I will give you one extra hint here at this stage here. The ideal way to consider it is as a pair of electrons. I want you to consider why is it that a pair of electrons, which is capable of showing many different resonating structures, where obviously one of them is going to be the most stable, but the remaining are all less stable, but it is gaining stability through moving into the other structures. What is it
Hmm.
that the pair of electrons is gaining more clinically? And what is happening here? And I would like you to consider that pair of electrons a little bit more closely. Try to
Hmm.
understand what a pair means. Consider that question first, then try to consider the remaining things. Ultimately, it's all about what to say. If you break down the question to a lower by a lower by a lower by lower level and start questioning the assumptions, ultimately, what are we questioning here? What am I asking you to question now? I'm asking you to question the assumption which you're able to feel in your bones, literally.
Hmm.
And I'm asking you to question that assumption at the lowest level possible, which is at a pair of electrons. Because ultimately, what are we made up of? We are made up of a bunch of those pairs of electrons acting in synergy in some way. Right. So
Hmm.
effectively, I want you to consider that question at a core level now. So start considering what are the pair of electrons? What does it mean to have a pair of electrons?
Hmm.
That is where you should start from. Okay, now that is a question for later. Let's come back to things. This question after your entire aromaticity has been discussed, and after you got a little bit more data.
Hmm. Yeah.
Okay, now let's go back to what else is left over in the current syllabus here. So we have this and put down in order, so to say. I want to start ticking them off as I'm going through. So I'm having cyclohexane, and I'll be having cistrons in this. What else do I have?
Silicon formula. Stability of conformer.
Be a bit more specific, na?
Stability of conformer.
Okay. All right. And what else? Next. See, the stability of conformers will come into the picture now in cyclohexane and cistrons also. So we'll start with somewhere over there itself.
Hmm.
Any other pieces?
Uh, that's about it.
No. It will not be rude of me not to ask this question. Have you got your 100 to 150 questions done in this current week?
No, sir, not yet.
And when are you planning on getting them? What is your count at right now?
So I'm at like somewhere around 50,
What is your count at now? 50.
somewhere around there.
And when do you plan to finish this remaining 100 by?
This weekend, sir. I mean, I have a holiday tomorrow.
Oh, 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 okay, okay, okay. I understand now. I understand now. You understand this week by Saturday you should be at 300, right? You owe me 300. And I'm going to be as sincere as Brad Pitt in Inglorious Bastards. I want my scalps. I'm not kidding. I'm being very honest. I'll harass you every time. I want a count on a class by class by class basis. I want it to see as like properly it has to go up.
Okay.
And I want you to meticulously maintain which questions you have worked on.
Okay. Yeah.
You understand?
Yes, sir. I'll do that.
Because this is necessary. This is necessary. There's no escape here. The kids who you see who have come up, they have done this before. That's why they are there already. Or
Hmm.
they have not done it in this concentration or in this intensity, certainly, but they have done the quantity over the large amount of time. That's even better, actually. Right? It's like slow aging, reversible process is always more good for the brain.
Yeah.
This year, what you're going to be doing is you've done thermodynamics, no?
No, sir.
No, not yet. But they're starting organic. Fuckers, what the fuck are they doing?
So we have online classes tomorrow.
Sorry?
We have chemistry online classes because we are very behind in syllabus.
You're seriously useless fuckers. I mean, I don't understand what the fuck they're doing in your school there, really. This is like this is December. They're not even touching, you've not done equilibrium. Equilibrium is like done to some extent, I suppose, right?
Yeah, we finished equilibrium
How they did this
completely.
crap. Thermo is not done.
No, sir.
Oh. So they are going to be starting online classes also.
Yeah. Tomorrow and day after we have.
When you say online classes, explain.
Like, I mean, we haven't had many online classes before. But like, I guess I'm not sure exactly. I mean, they just teach online.
One to many,
Zoom.
basically, I suppose, right? Normal
Yeah.
online.
Yeah.
Then there's nothing much different than pretty much the same thing as what we are doing over here. But you guys are basically the problem with your batches is that you guys are a COVID hit kid set of kids. But they will not give you guys the COVID hit privilege for long, dude.
Mm.
You're in 11th. The current 12th batch has been given extreme privilege. You can see that they have removed a bunch of syllabus in JE mains.
Yeah.
But you know what JE advanced did?
Mhm.
They just showed the finger nicely and left it to the side there. But you
Yeah.
get settled anyway. There's no escape there. They have to. This particular relaxation is for the COVID kids.
Mm.
There's no other way to look at it. The relaxation will go. So, huh. Anyway, coming back to the chemistry bits here. What else is missing? What else is a piece which is shaky?
That's about it.
Have you tried questions in the topic so far?
Yes, sir. I have.
And where all are you finding it complicated to pick up?
So mainly this confirmations.
And what else? Confirmations, I know, is a big issue.
Yeah,
That is going to be inevitably there. Other than confirmations,
that's
okay. So let's
that's
start
mainly
off.
it.
What do you understand by stereoisomers first? What
Serious.
do you understand by
Well,
stereoisomers?
they're isomers in which are differing by like uh yeah difference in the spatial
Let's first
arrangement
start
of
off.
atoms.
Let's first start off with what are we comparing? You're comparing
The
two structures on paper.
yes, sir.
Do these two structures represent the same compound or different compounds?
Same compound. Oh, no, 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 different compound, but same molecular formula. Sorry. Yeah.
So, two different compounds.
Yeah,
What is same?
their
Same
molecular formula.
molecular formula. And what else? And what else? If they are stereoisomers,
Structural formula.
structural formula. So, same structure. What is different though?
Arrangement of atoms.
Be more specific.
Spatial
Different
arrangement.
spatial arrangements,
Yeah.
which are non-interchangeable. Why are these non-interchangeable? They are non-interchangeable mainly because there is an energy barrier. What do I mean by an energy barrier? A bond has to be broken.
Hmm.
It doesn't have to be a bond has to be broken. It has to be something similar to a bond being broken, right? That is the basic understanding behind what is happening over here. Is this chain clear in your brain now?
So, but then why would there be an energy barrier? Shouldn't both have same energy?
Sorry?
Shouldn't both the compounds have same energy?
Repeat as to what you understood from that chain there. Have a look at that chain again.
Yeah, you said that different
Okay.
spatial
So,
arrangements. So,
what did this mean here?
certain amount of energy must be required to
Explain again. Think. What does energy barrier mean?
like in order to cross that barrier, you would have to supply some certain amount of energy. Pretty much.
Basically, if I want one of these diastereomers or stereoisomers to become its other stereoisomer,
Ah.
I will have to actually break a bond from some place and re-stitch the bond.
Hmm.
Maybe from a different direction, but I need to
Okay,
re.
okay, okay. Understood. Okay, okay. Yeah, yeah.
You
Got it.
understand the point over
Yes,
there?
sir. Yeah, yeah.
So whether it is going to be a cistrons or whether it is if it is cistrons, I'm going to have to break either the ring wala situation. One of the bonds in the ring has to be broken and then restitched. Or I'll have to break the pi cloud alone and then restitch.
Okay. Yeah.
In the case of optical, what will happen? I'll have to actually break a sigma and then reattach it from the opposite direction.
Yes, sir. Yeah. Hmm.
You're understanding what I'm trying to explain here.
Yes, sir.
So there is always going to be an energy barrier.
Hmm.
Breaking the bond requires energy. Correct. So
Yeah.
there is
Yes.
always going to be an energy barrier preventing one structure from becoming the other.
Okay. Yeah.
Is this part properly clear now?
Yes, sir. Yes.
This is the micro level flow which is going to be applicable when it comes to what is to be understood by stereoisomers. Now,
Hmm.
to understand stereoisomers most effectively, you need to understand spatial arrangements in three-dimensional molecules.
Hmm.
All right. When it is up to 2 dimension, it is acceptable. Things are going to be reasonable. If I remember correctly, I had also discussed and confirmed that your teacher has already discussed that any ring
Yes.
which is going to be, what to say,
One
8
equally.
or higher, there he seems to have already talked
Huh.
about the ring wala planarity conditionalities and what
Yes.
how
Yeah.
those things work out. I
Yeah.
remember testing it out using the double bond wala thing in the ring case last time.
Yeah.
So if
Hmm.
your teacher has given that 8, he would have discussed everything else related to the 8 there.
Yeah.
Yes.
Yes.
So you guys know that a 5-membered ring is going to be having one carbon out of plane.
Yes.
And in a 6-membered ring, you're going to be having two
Two.
carbons out of plane.
A half chair.
So you're going to be having two carbons out of plane effectively. In a 7-membered ring, more of them. 8-membered ring as well, more of them. So effectively, you're going to be having different shapes applicable.
Hmm.
Now, let's go to your 6-membered ring and start off with things there. Now, before we go into the 6-membered ring, let's quickly touch upon this conformation stability part here. Why do you feel lost over here? Give me examples of what made you feel lost there.
Sir, I sent you a question. Can you see that?
Yeah, I'll have a look. See, the problem is you're banking too much on your eyes. I hate to sound like one of those stupid little Jackie Chan wala shitty bastards who is trying to be as cryptic as they can be in their in the way they sound. But yeah, I am as cryptic as I need to be. This is unfortunately a very shittily written question. Organic chemistry, you're going to be having huge number of questions necessarily available. You're
Hmm.
going to find shitty errors in questions, very stupid errors in questions. You're going
Hmm.
to have to stop seeing with your eyes and start seeing a little bit more with your brain. You have to start guessing what could have been the question, what should have been the question, what is it that I'm not looking at correctly over here, and what to say, start guessing around. Now, I'm 100% sure your teacher has taught about intramolecular hydrogen bonding possibilities.
Yes. Yes. Here that happens. Yeah.
Only stupid problem is you don't see the neighboring carbon here.
Hmm.
This is the goddamn problem. You see the thing now?
That's to be three.
No, there is a CH over there. It is not a CH2. So there is CH3, CHOH, CH2F. This is carbon 1, this is carbon 2, this is carbon 3. This is the structure.
Oh, but why should be like that?
Because that's what the question is.
But
Because
why
that's
can't
what
you
the
do
question
that?
is. Look at the question. Which conformer of the above carbon is compound is most
Oh,
across C2,
C.
C3?
Two, three. One more carbon should be there. Oh,
No, not one more carbon should be there.
then
This is C2 and C3. The answer is supposed to be gauche, right?
yeah, it's gauche. Yeah.
Yeah. So what the problem was what over here for you? It didn't make sense, right?
Sir, if the OH and F are closer, like fully eclipsed, shouldn't there be a strong hydrogen bond?
Oh, you actually had a doubt with respect to the stuff which you learned in your school itself. Ah, okay.
Huh.
You had a doubt with why the gauche is more stable then.
Yeah.
Okay, that is your real question there then.
Yes. Yeah.
Oh, that is fairly easily solved. Sorry, I thought your issue was basically that this question looked weird. And there was another mistake in the question here, so I jumped on the obvious mistake there. My mistake here, sorry.
I didn't notice that. Yeah.
So you didn't even notice that there was an obvious mistake.
No.
Okay. So you have already blinded yourself to this. Good enough, not bad. So you're already seeing with the sight. That much pain you have felt then. You've been humiliated badly than these 2 3 weeks in chemistry. Interesting.
Yeah.
My solution is very serious. I was not kidding about your 150 questions in a week. You have to start getting there.
Okay. Yeah.
There is no escape. I'm not even kidding about it. You owe me 300 questions by the end of this 30th. You understand that, right? That is last week. I'm counting it as last week. Bhad mein jaake, I only started the class from Tuesday or Wednesday. I'm not going to count it from that point of view. Yeah, tera week hai wo. So you owe me 150 for that week. And this week starts tomorrow. Take not tomorrow. You can count it from Monday or whatever. I don't have a problem. But you owe me by Saturday before your Sunday class next week. You owe me at least it has to be at 250. Let it not be at 300. It has to be at 250. You can have like 50 for that Sunday. Not a problem. But it has to be at least 200 to 20 plus minimum. I hope I'm very clear here. I don't care what questions you solve. I basically want the numbers basically. What did I tell you? This is grinding.
Yeah.
I really don't give a fuck what questions you solve. Find the easiest questions you can solve. I want numbers. If you find the most shittiest questions, bad choice. I'm not even kidding. That is the attitude you have to start showing now. First bunch, collect the data about what type of questions are asked. Because you do not have data on that yet. That is where you are lacking. Understanding, you'll catch up. But this kind of experiential data, there's no way you can catch up without grinding the bit out. So start grinding. Confirmations here for the gouge part. So let's start off with that. So what is going to be happening when you are going to be having a confirmation, which is called as gouge? So let's start off with the basic one itself. We'll take with hydrogen and OH. So this is the one you guys would have discussed in school, I suppose, right? Ethylene glycol.
Yeah, ethylene glycol. Yeah.
So ethylene glycol here, you're going to be having the gouge conformation being the most stable one. So your question here is, why is it that the gouge is more stable? Why not the eclipsed? Why not the other ones? Why is it that it is not going to be that? Right? So now, whenever you're going to be having a question of this sort, what is going to be the issue here?
The hydrogen bond.
Good.
Like, yeah.
So what have I taught you so far? Till now, when you're having something like this, a question, this is a deep question, right? When you're having a deep question as a problem, what should be the problem? Where will be the problem?
Assumption.
Good. What is the assumption you have to start now questioning? You basically told me already.
Yeah, when it's eclipsed, it should have hydrogen
Not
bonding.
that hydrogen bond.
Oh, hydrogen bonding. Yeah.
That is what you need to start understanding a little bit more carefully, because there is a hidden assumption here, which is mostly going to be solving my problem here. Right?
Yeah.
Because everything here has to do with hydrogen bonding.
Correct. Yeah.
Right? Everything here has to do with understanding hydrogen bonding. And there has to be some assumption here, which is putting a curtain in front of my eyes here. Which is why I'm not able to clearly understand what is happening here. Because the only concept here is hydrogen bonding, and something behind it is sticky. So let's go for hydrogen bonding assumptions. What is hydrogen bonding? What is happening in it?
weak bond between a hydrogen and an electronegative atom.
Repeat.
Bond formed between a hydrogen and an electronegative atom.
I did not want that answer. That's why I told you to repeat.
Oh,
When I'm asking you to repeat something which is obviously seeming correct to you, it's not that you're wrong. I just don't like that answer. I
hmm.
want you to rephrase the same thing slightly more carefully. I remember I discussed a little bit on hydrogen bonding with you.
Yes, sir.
So, why is it that the hydrogen specifically attached to the electronegative atom is the one which is showing? What were the two things I would have discussed on hydrogen? I remember I would have normally, if whatever, however much your teacher does in your school, I would have discussed these two things. I would have talked about ammonia, water, and HF. Yes or no?
Hmm.
Comparison of boiling points. Did we discuss that or not? I mean, from
Uh,
the point of view of which one has higher boiling point and why.
yes, sir. We did that. Yeah.
Mm.
I
So,
guess we
what
did.
is happening there? What was the logic there? Which one has the highest boiling point among the three?
Sir, NH3 has more hydrogen bonds, so NH will have more. No, you said something on it. Wait. What are the compounds again?
The logic you remember is correct,
But you gave priority for that.
but you
Wait.
basically stopped thinking beyond that. How do you decide what decides the number of hydrogen bonds? Which guy has maximum number of hydrogen bonds? Water, NH3 or HF?
NH3. No, sorry, H2, H2, H2.
Why?
Because it has two.
What is the
No,
necessity for a hydrogen bond?
hydrogen.
What is a hydrogen bond? What do I need?
Between
You're
lone pair
starting
of electronegative atom and then hydrogen.
needs to be clicked now. So, what is a hydrogen bond? Come back to what is the assumption I'm asking you to question now. What is a hydrogen bond? Be as specific as you can.
The bond between a hydrogen and the lone pair of
Interaction between what? Do not call it a
hydrogen,
bond. Interaction between
hydrogen and lone pair of electronegative atom.
hydrogen. Be more specific. What type of hydrogen?
Bonded hydrogen.
What type of hydrogen? Hydrogen with a very high delta plus.
Oh, yeah, correct, yeah.
Right?
Yes,
That is the bare minimum requirement here, correct?
yes.
Interaction between a hydrogen with a very high delta plus and what else?
Lone pair of electronegative atom.
Again, be more specific. Lone pair of what?
Delta minus. Atom with delta minus. High delta minus.
Be more specific. In the discussion which we had talked about in hydrogen bonding, I will discuss only two sets of examples. I will discuss the H2O, HF, and NH3
NH3.
to signify and make your assumptions crystal there as to what is a hydrogen bond. Then I would have discussed about how you're going to be looking at only second period elements with delta minus. Right? I would have discussed something related to that. I would have talked about carbon being capable of showing. I would have probably touched upon chloroform.
You told carbon. Chloro is something you told.
Right? So I would have discussed about why carbon is going to be the significant other which is possible, along with nitrogen, oxygen, and fluorine. Why not? Why not chlorine? Why not something else?
Yeah.
What was the reason?
Size.
Good. So effectively, the idea there is it has to be a second period element. So the lone pair has to be in the goddamn vicinity.
Okay, understood. So it should be lone pair
between the lone pair and the hydrogen delta plus is critical there. That is the other significant thing which you need to start understanding. So effectively, let's go back. Lone pair of second period delta minus species. All right. Now, let us now look at the other thing which I was very strict about. When you said bond, I got pissed off. I asked you to basically call it as an interaction.
Yeah,
Why?
it's not a complete bond.
What do you see? The problem which I had was not with that, with anything else. I had a problem with bond. What does a bond mean? When you are going after core assumptions, you should never define random things and make assumptions there. Extra assumptions there, extra definitions or extra assumptions there. We have enough assumptions here already to play with. What are the assumptions we still have left? We still have what is mass, what is charge, how do they interact? All of those basic assumptions are still left over.
Yeah,
We are not through the assumptions yet. So now let's not add extra assumptions of bond over here. So a bond effectively is something which is a strong interaction, strong
strong. Yes.
attractive interaction. As simple as
Hmm.
that. Correct. At the end of the day, it's an
Hmm.
attractive interaction between the two species. So in this particular case here, a hydrogen bond is going to be an interaction which is not as strong as a bond in all cases. It is something which may become reasonably stronger. And this interaction is going to be something where it is a KQ1 Q2 by R squared type of interaction only. Like
Hmm.
every other interaction. It's a covalent bond, it's an ionic bond, it is a H bond. I don't give a shit.
All governed by the same thing. Yeah.
Resonance, whatever the fuck you want to look at, all are interactions between electrons, which means all are governed by KQ1 Q2 by R squared or KQ1 Q2 by R.
Hmm.
Governed. I hope you are seeing the other hints which are coming over here. I'm not going to be stressing upon them beyond a point. So all are governed by the same system of equations. Now,
Yeah.
how you understand this, that is different. How you interpret it is different. Now, coming back to this particular part here. So when I said it is an interaction here, why is it that this is not comparable? If I'm going to be linking up these stuff which you are already supposed to be familiar with, ionic bond, covalent bond, and all of those. Let's try to
Hmm.
link them up and try to see all these together now. So if I'm considering an ionic bond, in that there is going to be Q1 and Q2 having full blown charges. Where it can be a plus some electron worth of charge or plus some x into electron worth of charge. Q1, like say sodium plus, now it will be one positive charge.
Hmm.
If it is calcium 2 plus, it will be two positive charges.
Two and two events.
So Q2 also is going to be something which can be a negative electron charge or it can be some y into negative electron worth of charge as well.
Hmm.
So this is also going to be multiple possibility. This is for ionic bond. And the distance is also going to be tremendously lesser in the ionic bond case. The R value is going to be lesser because the ions are more strongly attracted. So it'll be
Yes.
closer together as well.
Yeah. Yeah.
So in the ionic interaction, this is smaller. The Q1 and Q2 are larger. Correct?
Overall forcing.
Let's talk about other types of bonds now. So that is going to be the best type of interaction. That will be the strongest. The next one which is going to be at play is of course going to be polar covalent. Correct?
Yeah.
In a polar covalent, the fellows are already bonded by a bond. So they're already chained together.
Yes.
Yes, they are chained at a distance, certainly. But they are chained already.
Yes.
And they are having delta plus delta minus.
Hmm.
So the charges are not that heavy, certainly. Not by a stretch. Not by a huge stretch. And you have learned that in a bond like H and F, where the electronegativity difference is how much?
Like approximately 2.1.
Good. So you remember from chemical bonding that there are only like 3 or 4 pieces of data. Your teacher would have given you an electronegativity as well.
Yeah.
Which ones did he give you?
Fluorine is 4.0, and then uh, hydrogen is 1.9, I guess.
2.1, but go on.
And then this what's this one? No, nitrogen is 3.7 something. The oxygen is 3.7, I think.
3.6, 3.5, 3.6. Nitrogen and fluorine are approximately 3. And you're
Three.
going to be having carbon at approximately 2.5
2.6.
and
Yeah.
2.55, 2.54 kilopascals. And you'll be having, other fellows, other halogens below 3.
Yeah.
2.8.
Below.
That's the goal.
Yes.
That's all you
Yeah.
need to know in the electronegativity values. So now, why those?
What? Can you repeat?
Why those?
Oh, because.
Values are to be learned so that you connect the pieces here. And in
Hmm.
organic, wherever necessary. The carbon and hydrogen values are given to you for the organic bits there. Carbon and
Hmm.
hydrogen bond, if you're looking at a CH bond, what is happening? The value which was given to you, which is going to be 2.55
5,
something,
6. Yeah.
that is going to be for an sp3 hybridized carbon.
Yeah.
All right. So when you're going to be going from sp3 to sp2 to sp, you're having
Hmm.
increasing percentages character,
Yes.
which means increasing electronegativity. I
Yes.
think we had already discussed that bit a little bit while back when one question I had,
Chemical.
I would say, I think atomic structure case upset. I think we had discussed penetrating power associated with that.
Yeah.
Yes.
Yeah. Yeah. Yes.
So, all right. So now, yeah, that is going to be the piece which will connect over here. So if you're going to be having, say, a carbon which is going to be sp hybridized, you can think of it as close to 2.6 and a half, 2.65, 2.7 KSPAS,
Hmm.
electronegativity wise.
Yeah.
Now, however it is, HF bond barely has like 30 to 35 percentage ionic character. HF, right? And in HF, you're having what to say an electronegativity difference of 2 to 4. So when you're going to be considering polar covalent bonds, that is going to be the most polar covalent bond available, and that is going to be having the maximum polar covalent attraction possible. And even in that case, the polar covalency is approximately going to be like only 30 to 35 percentage. So
Hmm.
polar covalency is nothing compared to ionic. Ionically, the R is going to be so much more smaller, and you're going to be having the plus and the minus. The quantum of charge is going to be so much more higher. So that is basically the difference between ionic and polar covalent. Now consider your hydrogen bonding. This is like some tiny crappy bit which is like nothing.
Hmm.
Unless and then there are circumstances which decrease the R value here significantly. You're never going to be having the hydrogen bonding being as effective as anywhere near even a weak covalent bond. So if you want the hydrogen bonding to be more effective, you need to have the hydrogen bond happening between a hydrogen which has a high enough delta plus first. Some other species which has enough electron density also. Happy enough to give. Delta minus should be high enough that it can happily give away. And furthermore, distance has to be brought in as much as possible in an artificial manner, at least as close as possible.
Hmm.
That is the basic requirement. Now, are these features clear so far?
Yes, sir.
Now let's go for the real KQ. Let's go for the real actual thing there. So when you're going to be having the structure, so let's draw the structure. The reason why it is a little bit more confusing to understand is because you can't imagine the spatial orientation properly. So let's go for Newman projection. I'm assuming you have been taught
Yes.
Newman projection by now already, yes?
Yes, sir. Yeah. That's what I. Yeah.
You know how to represent this in Newman projection, yes?
Yes.
Do you know what representing in Newman projection means?
Yeah.
So let's take a simple carbon-carbon system. So let's take this as your what to say ethylene or that's
Hmm.
ethane. Okay. So ethane, if I'm going to be looking at the conformations possible, Newton projection is going to be something where we have a front carbon and a back carbon. So
Yeah.
effectively, this is the same thing. You're going to look at it from literally the point of view which you're looking at it through now in the camera. So you're going to be having a front carbon and a back carbon point of view. This carbon is going to be the front carbon. This carbon is going to be the back carbon from your perspective. So the front carbon is going to be represented as a dot, whereas the back carbon, which you cannot see, is going to be represented as a circle. All right. So front guy is the dot and the back guy is going to be the circle. The front guy's bonds are literally going to come from the dot. The back guy's bonds will come from the circle. Fair enough?
Yes.
So
Yeah.
let's start with that. So we're going to be having front and the back. Now, I'm assuming you have already got familiar with Y inverted Y. All of those are fairly clear.
Yes,
Eclipsed
yeah,
and staggered are perfectly clear now so far, yes?
Yes.
Okay. So when you're going to be having staggered is going to be a Y and an inverted Y in such a way that the bulky fellows are completely opposite to each other. Such that steric strain is minimized as much as possible. So are you clear with what is meant by steric strain so far?
Yeah, somewhat.
Steric strain basically means fat groups which are present. Think of it like any system which is going to be electron rich is going to be requiring some space to put those electron densities. Because electrons inherently hate each other. All right. So electrons hate each other. So when you want to pack a set of electrons in a space, you need to make sure you're providing sufficient space to pack those electrons in.
Okay.
If you're not giving enough space, you are basically creating a region where there is going to be some instability there. Some repulsions are there, which is chaotic. Okay, now let's get to this part here. So I'm assuming your understanding about staggered is clear. That means you understand also what is meant by gauge. What is meant by gauge then?
The bulky groups are next to each other. Next to meaning
more clearly, please. What is meant by gauge?
The bulky groups are at the
No. Oh. Let's start with what is gauge first from the real perspective. Gauge is a form of staggered.
Oh yeah.
But not completely.
Yes.
Fair enough. So think of it as it is a form of staggered conformation, but it is not a completely staggered conformation. It is anything in between, technically speaking. All right. Anything in between, you call it as gauge. That's the truth. Okay. Now let's start understanding what this means here. So in this particular case here, what is happening is this is one carbon, this is another carbon. We are having hydrogen and hydrogen here, and we are having hydrogen and hydrogen here. They are telling us if I'm having a fluorine here and an OH here, or let me write it a bit more clearly. If I have an oxygen here and a hydrogen here, they are basically telling you that this interaction is better. Correct? Yeah. Compared to if I'm going to be having something like this.
Yeah, that's it.
I mean, your issue is something on these lines, correct?
Yeah, that's it. Yeah.
This looks closer.
Yes. But is it maybe because of the bulkiness?
So, this is where the assumptions behind the question need to be challenged. Why did I ask you to go through the entire bit of hydrogen bonding? What was the entire purpose of that storytelling there? Can you now guess? What was the point I was really interested in driving home completely? I told you a story, right? I took you across a story. Summarize and tell me which point was a superhero point with respect to the continuation of our story now. Do you understand what I'm
Solid.
asking?
Yes, sir.
Now, so what did we do? I sat and summarized hydrogen bonding for you,
Hmm.
right?
Yes.
Special emphasis on some points, the overall assumptions. Now, in today's lesson, which guy is the champion? Which point is the one which we are looking for closely?
Interaction.
You got the direction where you need to go correct over here. Now go deeper. Which point in the interaction was I really interested in stressing on?
The lone pair of second period.
True, but more specifically, please.
Oh, it should be small. Oh, but no, 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 nothing.
I'm interested in the space.
Space.
That is, the R value has to be as low as possible because we are never going to have the Q1 and Q2 ever being sufficient enough here, right?
Correct. Yeah.
That is never going to be happening ever. But the only way to basically look at it is the R value has to be smaller.
Hmm.
But now the next question becomes, what is that R? What is that R? The R is this.
Distance between these two. Yeah.
So now we need to start seeing where are these two guys. So is it the fluorine which I should be really looking at drawing over there, or what should I be looking at drawing there? I should draw a lone pair of fluorine and then check
Yeah.
truly what is the distance there.
Correct. Yeah.
You understand the point now?
Yes.
So let's put that and see. So if I'm going to be considering an OH, I can imagine an OH group like this. An oxygen is going to be technically tetrahedral as well, correct?
Yeah. Yes.
Right. So that oxygen fellow is tetrahedral, but the guy has got two lone pairs.
Hmm.
Correct?
Yeah.
So I'm going to take this as an oxygen. Another tetrahedral fellow. Okay. I'm going to connect that guy to one of these locations.
Hmm.
Fair enough. So this was my original carbon and carbon. But this fellow, which is going to be having the blue fellows are lone pairs. So this is not a carbon, this is an oxygen now actually.
Yeah.
And this
That's
guy
a
is,
hydrogen. Yeah.
you understand the point now?
So, but we need to focus on the
Calm
lone pair
down,
of.
calm down. We are not done.
Okay.
We are not done. This guy represents a fluorine,
Mm-hmm.
the red fellow. All right.
Yeah.
And this blue guy represents an oxygen. All right. So let's start. So the blue guy here, I'll put a white fellow for representing the hydrogen on it. Okay. So the blue guy has got two hanging and a white. Yeah. So this is going to be the carbon where the OH is attached. This is the oxygen. Oxygen has got two lone pairs, as you can see. These two which are hanging as it is are lone pairs. This white fellow is your hydrogen. This guy is the one which will do the hydrogen bonding. Yes?
Yes, sir.
Okay. Now, this is my fluorine. I'm going to connect the fluorine directly onto the neighboring carbon. I'm going to connect this fluorine directly onto the neighboring carbon here. All right, so this is how the flow looks now. So now, this is my eclipse conformation, correct?
Yes.
In this eclipse here, if I rotate it like this, what you're basically saying is I'm having a good interaction where
Small
these
distance.
guys are as close as possible.
Yeah.
Right?
Yeah.
This is the argument here.
Yep.
Yes or no?
Yes.
Well, now what is the problem which happens over here? You're having repulsion between these two guys. You're having these repulsions. And most critically, you're also going to be having these guys are also going to be repelling each other. All of them are going to be repelling.
Hmm.
Remember, lone pairs are not going to be occupying small amount of space. They are going to occupy a tremendously large amount of space. Because lone pairs are like fat fellows, correct?
Yeah.
Because you're only attracted on one direction, not on both directions. So now let's rotate this guy slightly into a gouge conformation. In this gouge conformation, as you can see here, this is a gouge where I'm going to be having this as the fluorine here. As you can see, the fluorine is in a type of what to say inverted Y, and the back fellow is in a Y over here.
Yeah.
Correct. So the front is going to be inverted Y for you, and the back is in a Y conformation. This is a gouge conformation. So now in this gouge conformation here, have a look. If I rotate things suitably, I can get my hydrogen
Minimum
and
distance.
into a direction where they are now nicely close enough, which is similar to the distance between the hydrogen and the lone pair in the previous case.
In fully eclipsed. Yeah.
Right? It is
Yeah.
not as perfect, but it is very close enough.
Hmm.
But remember, flexibility is allowed everywhere in this game here. When I say flexibility, you remember the CLF3 case in chemical bonding?
CLF3.
Chemical bonding, we would have discussed only very few structures, correct?
Yeah.
But I would have touched CLF3 for sure. I would have discussed the three different possibilities over there. I would have discussed basically talking about how the angles are different in each of those cases.
Okay. Yeah.
I would have
Keeping
used
one
probably an analogy
in the
using
center.
the pain centers with respect to the angle there. That applies here as well. The game goes like this. When you're going to be having something like this, you want to minimize the distance between them. But what is the true goal of hydrogen bonding at the end of the day? Go back to the true goal of what hydrogen bonding does. It increases stability of the molecule.
Yes.
So, if I am going to be bringing in a hydrogen bonding, the purpose of bringing the hydrogen bonding in is to increase the stability.
Yeah.
Correct? So, when I'm going to be doing this intramolecular hydrogen bonding, the ideal circumstance would be the best hydrogen bond possible is not the one which is going to be the one which is going to be closest for me, but it is actually the one which is going to be increasing my system stability to the greatest extent.
Okay. Makes sense. Okay.
So now you will have to start considering the hydrogen bond from, okay, this guy requires this parameter, but at the cost of not screwing the other systems beyond a point. In the eclipsed conformation, what is happening over there is, yes, you are having distance between the hydrogen and the lone pair of the system being as close as possible. But it is coming at a cost. The cost is you are making sure that every other bond is eclipsing the other. Which means increasing all of the other repulsions at the same time.
Oh, okay. Understood. Even though hydrogen bond is stronger, the others will.
Correct. That is what you are doing is you are making sure that the hydrogen bond is at the closest distance possible. Yes.
Yeah.
But it is coming at a cost at the other cases there. Because all of the other guys are also now having slightly greater increased repulsions.
Yeah, correct.
So it's like, yes, the boil on your ass is now most comfortably situated. But the rest of your ass is sitting on slightly thorny regions.
Yeah.
Understand the idea here?
Yes, sir. Yeah.
But the problem here is this. When you go into the gouge there, it is not obviously clear that the distance between the hydrogen and the lone pair are actually very similar still.
Yeah, that's what I was thinking.
That's why I wanted to show that to you. You could see they are very close by actually.
Yes.
When you tilt them in right angle, they become very close by. Would you like to have a look at that again?
They're not. There's no guarantee that the lone pair is that
Did
close.
Did I finish my discussion here? Stop. What was the other point I talked about there? CLF3. What was the lesson in CLF3? You fucked up in
So
your exam. What was the fuck
yeah.
up you did?
So the angle, like, which is
Good,
this bond
good,
angle.
good. What is happening in real life? Mathematically, whatever you decide is not going to be followed. It will
Hmm.
bend and it will do shit. In this case, that's what it will do as well.
Okay.
See, it's like
Understood.
this. One guy has to bend slightly away to increase the interaction between the hydrogen there. That's all right. One lone
Yes.
pair has to bend. A lone pair is already only connected on one ending to the nucleus. It is very bendy. That is
Yeah,
why it
it's little
occupies a
bit.
lot of space, correct?
Yes.
In the first place, the lone pair is something which is a very large group. It occupies a lot of space, mainly because it is only attracted on one end to a nucleus. The other end, it is free. If it's a bond pair, what's the system? The bond pair is having one nucleus on each end, right? That's what a bond
Yes,
pair
sir.
is. So
Hmm.
that's the reason why the bond pair is something which is going to be attracted on both ends, so it occupies lesser space. The lone pair is already only attracted on one ending.
Yes. Yeah, it has flexibility to move around.
Exactly.
Hmm.
So the lone
Okay.
pair will bend now quite comfortably. It's not a problem about it at all to bend.
Hmm.
So the one lone pair bending is far better than every other bond pair and lone pair adjusting, right? In that eclipse below
Yes.
there.
Yes. 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 Yeah.
So that
Hmm.
adjustment will happen here far more comfortably. You have to make room for tiny adjustment being possible in the final structure. Because just like how when you have a boil on your ass, you will adjust and wiggle your ass as much as you can to adjust
Yeah.
that pillow properly. Molecule will also do the same. Excepting in this case, the boil is not really a boil. It's a position where it gets more comfortable, that's all.
Yes.
A
Yeah.
pain center or a comfort center are both doing the same
Yeah.
at the end of
Hmm.
the day,
Yeah.
right? Energy wise speaking,
Yes, sir.
they're a bump in the energy. Either it's a bump up or a bump down.
Hmm.
Yes or no?
Yes, sir. Yeah.
No. Okay. All right. So let's come back to this here. So I'm assuming this is properly clear now
Yes, sir. Yeah.
and
Clear.
you'll not come back to this again.
No.
So whenever you are going to be having hydrogen bonding, intramolecular being possible between two neighboring carbons, you're going to be having the gauge conformation being the best possible one. Why? Because it is not just that the hydrogen bonding is as good as possible. Yes, the hydrogen bonding can be better, but the adjustments required will be much more in another structure.
Hmm. So, yeah. Yes.
In this structure, the adjustments required to have the best possible hydrogen bonding are very minimal, and the rest of the molecule is in its more
Happy state. Yeah.
correct. Happy
Yes.
state is not a bad way of looking at it. Correct.
Yeah. Yes.
That's the
Yeah.
basic way to look at things. Okay. So I'm going to assume this is properly settled now then. Yes.
Yes, sir. Yeah.
So your conformal stability, I'll cross this shit off.
Yes, sir. Yeah.
Was this the only problem you saw in your conformal stability issue there?
So far, that's it.
So far, nothing else. Okay. All right. Cool. You have become very, I think chemistry has basically taught you how to converse now more carefully. You're starting to use
Yeah.
more measured language. Okay. All right. Huh? Next was your cyclohexane. No?
Yeah.
Cyclohexane, we had just started discussing the idea here. So let's fill in the blanks here. What is a structure if it's completely planar? All of them have the
Oh,
same conformation. Either it is
yes.
y, 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 or it is going to be
Lambda. Sorry.
inverted y,
Drawing that inverted.
inverted y, inverted y, inverted y.
Yeah.
This is planar. Half chair is going to be something which is going to be a little bit of an awkward type of scenario. In a half chair, the structure will look like this. So in this here, you're going to be having so carbon 1, 2, 3, 4, 5, and 6. So 2, 3, 4, 5, 6. will be in one configuration, one will be in different. So in a half pair, you can think of it as Y, inverted, 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 or it can be inverted, Y, 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 Y. Half chair is also going to be, actually no, these three will be in same configuration. It's a weird one. This part will be in staggered, these three will be in eclipsed. That's the way to go about it. So you're going to be having not necessarily exactly this. It could be this. It could be different also. I think this is also fine. 1, 2, 3, 1 inverted now. This will be Y inverted now. Y inverted Y. I'm correct now. This is staggered only. This is eclipse. Between these two, it doesn't have to be staggered or eclipse. So there will be 4 configurations possible actually for half chair. So 2 up and 2 down.
Yeah.
So chair is going to be your the one which we just talked about here. This guy is your chair, perfectly staggered. Whereas your boat is going to be partially staggered. I'm assuming these two are reasonably clear now so far.
Yes, sir.
Okay. Now, let's start talking systrons now. Cyclohexanele, what part did you not understand? I'm assuming you had clarity up to the different conformations and their stability.
Yes, sir. Yeah.
I'm guessing you started getting lost approximately when he started doing systrons.
Yeah, that's it.
So, why did you get lost? What's the usual excuse I give you?
Assumption? No. Yeah.
No, it's always the same. Usually, it's going to be the same thing only. What assumption here? Which one am I going to ask you to question?
That cis will be always less stable, maybe.
No. That is not the assumption even.
Because of report.
Going too deep into the assumption here. I want you to question systrons. How do you define systrons? That is the question, right? At the core, something
Yes.
to do about systrons is funny. That's why you got confused. Fair enough?
Yes.
Is that a better way of putting it now?
Yeah, that's it.
So, effectively, something about systrons is funny. So, let's go to systrons. Define them, please. Let's go into the definition of cis-centrons. How do we define cis-centrons?
Cis, it's when two same atoms or same groups are attached to the same side of double bond. Same side of a bond.
Okay.
Not necessarily double bond.
Okay. Now let's start questioning the hidden assumptions here. Your definition is not wrong. You were careful enough to be as detailed as you could be in your definition here. So I can't fault you with that also now. So now let's examine what you said a little bit closely. You said across a double bond are basically be a bit more inclusive.
Any bond. Oh.
Any bond, there is an extra statement which you have to give.
Any bond which has different.
When I said inclusive, what did I mean really? You know about systrons in 2 cases already properly, right? You have done ring, you have done this. Double bond.
Yes.
Be inclusive.
Oh, ring also. Yeah, ring too.
Be inclusive.
Oh, in restricted rotation. Restricted rotation.
That is going to be conditioned for systrons.
Oh.
I'm not looking at conditionality. I want you to define the condition. What is it? The statement in a way in which it includes both. So what was interesting in the double bonded case? See, right now, what is the complexity which has been added in? Your definition was correct,
Hmm.
right?
Yeah.
But now in this case, an extra complexity has been added into the game, correct?
Yes.
What is the complexity which has been added in?
Confirmation. Like it can.
That's it. That's it. That's stop. You got the correct word there. Conformers.
Hmm. Okay.
Correct.
Yeah.
Now you need to start seeing in your definition of cistrons with respect to the double bond and the ring there, what were the conformers you had assumed them to be? Because you defined it in that case according to that situation, correct? At
Yeah.
that time, conformers you didn't know about. But does that mean conformers did not apply there? Or was it
No.
just that it was hidden?
Hidden.
So apply. Let's
Oh.
try it.
Okay.
Now calm down a little bit and start questioning your assumption a bit more carefully. Double bond, it is a little bit more tricky, right?
Hmm.
Why is it tricky in the double bond? Because they look the same,
Hmm. Yeah.
right? They look the same. But if I want to see conformers more carefully, where can I see it more carefully? In the ring,
Yeah. Correct.
correct? So let's draw a simple ring case. A simple ring case is this. And if I'm going to be having, say, hydrogen towards, methyl away, and if I'm going to be having hydrogen towards, methyl away, this is something which can be called as a cis. Is it
Hmm.
applicable or not applicable?
It is. Yeah. Cistrans applicable, but yes, it's cis.
Yes, applicable so
Yes.
far.
Yeah.
Okay, all right. So this is going to be something which will be the cis conformation here, right? Trans will
Yeah.
be the methyl will be on opposite directions, right?
H will be replaced with CH3. Yeah.
Okay, all right. So this is going to be having some hidden assumptions here, which are going to be hidden from which point of view?
Trigon.
Conformer point of view,
Oh. Yeah.
correct?
Hmm.
What are they? If I want to put conformers for C1 and C4 and C3, what will they be? What will the conformers be?
Different
What structure
structure.
is this?
Hmm.
What structure is this? The
What structure?
cyclobutane.
Cyclobutane. Yeah.
Cyclobutane, what type of a fellow is that?
Planar.
So if it's planar, what should it look like?
Oh yeah. Hmm.
Right?
Yeah.
So now, what is this then? This has to be something like this, correct?
Hmm.
That means these two guys are what really? What is the hidden assumption here inside the definition?
Same side of the bond. Oh, same conform. Hmm. Yeah.
Correct? Huh?
Yes, sir. Yeah.
That is a hidden assumption.
Yeah.
When you are having definition of cistrons, how do you define cis-centrons then? Define it more carefully now. When you are going to be having two carbons which are having inhibited rotation attached by a bond.
Hmm.
And in this system where there are two carbons which are having inhibited rotation attached by a bond, you are going to be having both of them in the same conformation.
Hmm.
And now, if the common groups are on the same spatial side, we call them cis. And now, if the common groups are on opposite spatial sides, we'll call them trans.
Spatial size. Okay. Hmm.
You understand the way to project the definition now clearly?
Yes, sir. Yeah.
by adding conformer into the bit now. Are you clear with what I'm trying to explain here?
Yes, sir. Yeah.
So till now, what did you have? You had definition of systrons in your brain properly.
Yeah.
Your confusion started when conformer was added into that definition without explaining to you how to add it.
Hmm.
Correct?
Yes, sir. Yeah.
So you need to clarify how to add this extra variable to a function which you already understand. That is a mathematical function. Systrons isomerism is a mathematical functionality which you have learned. To that
Yeah.
mathematical functionality, an extra variable called conformer was added. You did
Yes.
not treat it like that.
Hmm.
You saw this as the same systrons in different case. Wrong. It is systrons, but with an extra variable added in now.
Oh.
You have to start
Okay.
seeing what is the effect of that extra variable on the systrons definition.
Hmm.
On that black box as a function. Then you can now apply that logic now. So let's start. Let's say I'm going to be looking at cyclohexane now. So if I'm considering cyclohexane, when I'm defining systrons, I'm defining in planar. I'm not defining in some random structure which is non-planar. I'm defining in the planar. So systrons is something which is defined from a planar perspective, where all the fellows are in the same conformation. That part is clear so far, yes?
Hmm. Yes. Yes.
So now, before we go there, cyclohexane, when you discuss the other structures, the standard structures, and the basic ring flipping, I'm assuming till that ring flipping you understood.
Ring flipping means? Ring.
Discussed how the ring converts from chair 1 to chair 2.
Ah, yeah. It goes up like this. Yeah.
And you discussed the energy profile diagram for that.
Yes. Yes.
So I'm assuming you have done that twine, 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 twine.
Yeah. Yes, sir. Yeah.
And if you have discussed those, you would have discussed what is going to be equatorial, what is going to be axial.
Yeah. That's why I was kind of confused.
No, no, no. Let's not jump there. You would have discussed that.
Ah.
Okay. Let's talk about cyclohexane bonds now. If I'm having the cyclohexane in a, what to say, planar form here, right? So I will have one bond coming towards in each of these carbons. Correct?
Yeah.
And simultaneously, I will also be having one bond going away.
Yeah.
I'm simply going to call the fellows that are coming towards me as axial, other fellows as equatorial. I don't give a shit what they are. They're just names. One is one, the other is the other. I don't care what they are called. Sincerely. It doesn't make a difference. Let's not dwell on stupid names first.
Okay. Yeah.
They are terms. We'll get to why they are the way they are when we need to get to them. So for now, basically, one is towards, one is away.
Yeah.
Right? I'm just going to call the towards as axial and away as equatorial. Blindly, I'm going to name it. You know that axial and equatorial are opposite fellows.
Yeah.
That much is fair.
Yes,
Then
sir.
my naming currently is perfectly acceptable. All
Yes.
axials, all equatorials. Towards, away. Now, let's start trying to see things a little bit more clearly. In this current configuration here, we are having carbon, 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 carbon here. 1, 2, 3, 4, 5, and 6. So all 6 carbons here are in the same configuration. So Y, 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 or inverted, 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 inverted. Correct? That's what planar means.
Yeah.
So let's start with the cis. If I talk, say, cis 1,2 dimethyl,
Exactly.
what should that mean?
There are two
It should mean
methyls, yeah,
I'm going to be having
both at
axial
axial or
axial as
both at
methyls,
equatorial.
or I should have it as equatorial as methyls.
Yeah.
Correct?
Sir, but then it's half chain, no? Cis and
Cis. No, no, no. Stop.
oh,
Stop. There is no half chair sheet right now. What is
okay.
this? What are we looking at?
Just cis. Planar.
We are looking at planar.
Yeah.
All right, because I know how to define cis and trans only for planar.
Hmm.
Right? That's what my original definition of cis and trans is applicable for, correct?
Yes, sir.
Yes or no? Because
Yes.
ultimately, you have to start thinking what you define cis and trans for. Do not misunderstand that when you're connecting the pieces. We have cis trans as a function which has been defined properly mathematically. The problem came when we added conformer into the mix. Correct? So now we need to add the conformer in a very, 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 very controlled manner so that we can observe exactly what is happening.
Hmm.
Do you understand what I'm trying to do over here?
Yes, sir.
That's why I tried explaining that to you mathematically at that point. We are having a black box called cistrons, which has a certain set of functionalities, a certain set of rules. I have another black box called conformations. Originally, I had learned what this mathematical function called cistrons does under a certain set of circumstances.
Yeah.
I do not know how that applies in a different scenario. I want to understand that. Right? That's what we are trying to do here. But to understand that, I need to make sure I'm going back to the original definition with which I had defined it.
Yeah.
I will not taint that randomly without understanding the connection there. So I'm going to do it in a proper planar form. This is the planar one. All are in the same configuration. So if I have cis 1,2 dimethyl in this, all right, what is going to be happening is in the cis 1,2 dimethyl, my C1 and C2, if they are in the same YY conformation, then in that YY conformation, I can say this is going to be axial axial or equatorial.
Equatorial.
Because they have to be on the same goddamn side. Correct?
Yeah.
This is cis. Now, let me try to see what is going to be happening from a staggered projection if I have something like that. And try to observe what that means truly. So, this is basically YY conformation, correct? So, I have hydrogen here, hydrogen here, hydrogen here, hydrogen here. Let's say methyl here and methyl here. This is basically what's happening.
Yeah.
Right?
Yeah.
This is not hydrogen here exactly. This is going to be connection to ring. So let me rub this guy off. So this is not a hydrogen here. This is not a hydrogen here. This is a ring connection. Correct? I can
So we
imagine
can draw this structure for any two carbons, adjacent carbons, right?
we are not going to be looking for everything here. We are looking at one space. One place where we are looking. Stop thinking about the connections there.
Okay.
Zone in and try to see what's happening at this level here. Zoom in here. So there's some ring connection. I don't care what this is. This doesn't matter to me. Skip that shit.
Okay.
So these are in same conformation. This is going to be cis as of now. Correct?
Yeah.
Now, this is in the planar where they are both in YY. But in reality, your more stable structures are almost always going to be staggered.
Yes.
So you need to know what happens if I convert this Y to an inverted Y. Right? So originally, I basically had, this is what I'm basically putting the axial here actually. Correct? Because I took equatorial as away and I took axial as towards. That's the definition I took, na?
Yeah.
Right. So equatorial was supposed to be going away. Axial, I took it as towards me. So now let's flip this now. I'm going to take this as carbon 1. I'm going to take this guy as carbon 2.
But
If I convert this from a Y to an inverted Y for carbon 2, how will this be changing? I'll have hydrogen still here. I'll have methyl here on the axial. Correct?
Yeah.
This is ring nonsense. I don't care where this goes. This will become ring because this is going to be going inverting like this.
Yeah.
Okay. What will be happening to the other fellows there?
They will go down.
They'll basically invert completely.
Yeah.
So
It will
effectively,
be dash.
what's going to be happening is something like this. So I originally ended up having a group in this place like this, which is originally exactly in this fashion like this. So now I'm going to be rotating it and making it like this. So what was originally coming towards will now be inverted completely, correct?
Yeah.
You got that or not? I mean,
Yes, sir. Yeah, understood.
cool. So let me get out of this thing here. So when you're drawing it here like this, now this will be a CH3 and this will be a hydrogen. Meaning now in this carbon here, this is going to look like equatorial. This will look like axial.
Mm.
So
Yes.
what is the scenario here? This is still going to be C1, C2, correct?
Mm.
So if I
Yeah.
want to talk about cis 1, 2 dimethyl in a planar form, it is going to be equatorial, equatorial, or
Or axial, axial.
axial, axial. But if I change this guy from a planar to chair form,
Mm.
chair form is proper staggered, correct?
Yes, sir.
What should it become? It will become equatorial axial or
Or axial equatorial.
axial equatorial.
So when you change it to chair, they just swap. Like,
Yeah. No,
okay.
don't randomly swap though. No and swap. Because the game will
Why?
change in every stage.
But then here
Let's
it doesn't
show you
matter
here.
whether you put
Calm down, calm
axial
down.
and
You're starting to understand, but you're starting to basically randomly connect shit right now. Wait. Stop doing your random connections. First, come back to what are the various conformations. So if I'm looking at planar, planar can be written C1, C2, C3, C4, C5, C6. Can be
why,
written
why,
as
why,
Y,
why.
Y, 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 Y. If I take chair, chair is going to be Y inverted, Y inverted, Y inverted. Right?
Mm. Yes.
So now, if it is C1, C2, your definition is for planar.
Mm.
System's definition is perfectly the way you imagine it is for planar. Correct?
Yeah. Yes.
Same side is going to be the way it is going to be cis, opposite, not trans.
Ah.
Correct? Huh?
Yes.
Chair 1, 2, there is a difference. Where else do you see a difference? If I take C1, C4 combo,
Mm.
in planar it is YY. In here it is Y inverted Y. Correct?
Yeah.
So if I'm looking at cis 1, 4 dimethyl, then for the planar, I would have had it as axial axial or equatorial equatorial. Correct? Now if I
Yes.
flip this for chair, this is still remaining YY, but this Y is now becoming inverted Y.
Yes.
So what will happen here? It will be axial equatorial and
Or
equatorial
equatorial
axial.
axial. Mm.
Correct?
Yes.
But now try for 1, 3. If I have cis 1, 3 dimethyl, what is going to be the case? In the planar, it is going to be
Why, why?
equatorial or axial
Ah.
axial.
Yes.
Correct?
In chair also it will be same.
What should it be?
Equatorial.
Why?
Because they're always going to be the same
Both
thing.
are in the same conformation already.
Yes. Yeah.
You understand the rules to be followed here properly now and how to adjust them?
Yes, sir.
So
Hmm.
I'm guessing now your sys transfer the shit will basically start playing into clarity.
Yes, sir. Yeah. Hmm. Makes sense.
Now the next will be basically how to bring in both.
Yeah.
Same principle applies everywhere. Basically, the principle, if it is core correct, things will stitch nicely.
Okay. Yeah.
So in the board there, what's going to be happening? What is the
Hmm.
conformer for the conformation for the board there?
Both it will be
Hmm.
y inverted way.
Did I give it last time or not?
I don't think you did.
I would have. Yeah, I did. Boat I normally give. Huh, this is boat.
Yeah, that's what. Yeah, why? That's what I was saying. Yeah.
Hmm.
Hmm. Or reverse. Yeah.
Yes, it is not perfectly staggered, it is partially staggered.
Yeah. Yes.
That's the idea there. So for the board there, you have to be slightly more careful. C1 and C4 will be in same configuration. C2, C3, C4, C5, C6 will be in same configuration.
Okay. Yeah.
So this is basically the game behind this. Next, I'm guessing you still have a few issues with respect to this, which are going to be on the lines of why in some cases some fact groups are going to be present in some places more stably. Is that thing, have they asked questions on those lines already?
Yes. Yeah. Repulsions as well. Yeah.
Okay, all right. So effectively tertiary butyl crap or 1,4 hydroxy, that kind of crap has started.
Yeah. Somewhat. Yeah. Those stuff. Yes.
Okay, all right. Which ones we have as doubts? Because the fact is this, you're never going to be able to clarify all of them. Why? Because each of these individually is a special case.
Hmm. Sir, I
So,
mean, though.
yes, tell me.
Sir, so always the bulkier groups should be away from each other when no other stuff are at play,
See,
like
there is
charge.
no, see, how do you react? Do you always react the same way if the same stimulus is given to you?
No.
No. Then why the hell do you expect molecules to? You're a collection of them, dude. You're not going to be, means they are not going to be.
Hmm.
So never make hard and fast rules to follow in chemistry. You do that, you're basically fucking yourself.
Hmm.
Unnecessary. You're adding unnecessary bullshit assumptions.
Yes, sir. Yeah.
I started realizing by now that assumptions are the key game to really understand shit beyond a point.
Yeah.
Right? So if you really want to enjoy chemistry, you have to start questioning your assumptions. In physics, also,
Hmm.
there are a lot of assumptions. It's just that in physics, they are a lot more hidden.
Yeah.
And they know how to hide it very beautifully.
Yeah.
So, you have to start realizing what you want. And
Yeah.
for someone as intellectual as you cannot stand without understanding. It is not going to feel correct.
Yeah.
So, so let's throw that aside. Let's start accepting that understanding is what you want. And each case is going to be unique in its own way. There will be something
Hmm.
or the other unique. There are going to be some commonalities, but don't make the generalization the one which you have to remember.
Okay.
Remember that this guy is unique. Remember everything else similar to that guy is going to be similar. I won't care about it, but this guy is unique. So
Okay.
let me explain what I'm trying to say here. Do not make a generalization with respect to bulky group. Avoid making a generalization like that. Make a more specific generalization for alkyl groups if they are present. Don't call them bulky. If there are specifically fatso alkyl groups, MS Chauhan mein this exception is seen in 3 questions, which means my teacher has given me this exception in class. That is how the game works. So you are going to be having a bunch of exceptions which are going to be given to you one after the other in class. The way I'm sensing it, your teacher is very good at collecting these exceptions because he has been systematic about learning his subject over the years. He has not yet connected all the pieces perfectly, but your teacher has been very systematic about collecting these exceptions nicely.
The Gauss effect ones.
Yes, yes.
Yeah, those,
Practically
yeah.
almost all of these. I can sense the kind of things which he has probably given you.
Yeah,
I'm guessing
FF,
he's given you
CL,
tertiary
CL.
methyl exceptions. He's given you dimethyls. He's probably given you 1,4-dihydroxy, 1,4-fluorohydroxy,
Huh.
um, 1,2-dimethyl, 1,3-dimethyl. He would have given you. He would have
Yes,
given
yes,
you
yes.
1,4-tertiary butyl also probably. Um,
One,
all
four,
standard
three,
things.
better.
Anyway, so
Yeah.
point here is those are all like standard basic exceptions. If you have connected all of them together, then you don't need to give them individually. Things will, the connection is basically how to visualize cis centrons, how to connect
Hmm.
the cis centrons into conformer there. Because
Okay.
now you can see how they are supposed to be connected. Once you can see how they are supposed to be connected, then you can play the game. You don't need me to sit and hold your hand at every stage of the game now.
Hmm.
Now you know what is the way to flip, what is the way to get it done. Do
Yeah.
it, figure
Okay,
it
sir.
out.
Yeah.
Now I will give you this. The way to connect the pieces is when you are having a bulky group, like say tertiary butyl. It is basically something where there is going to be multiple connections drawn and multiple bonds. When I say bonds, multiple electron pairs which are specifically located in specific regions in space because they are bonded. Bonds are chains. All right. So you're going to be having multiple pairs of electrons forcibly located in specific regions of space. That is what a bulky group is going to be. So one bulky group and another bulky group obviously will want to be as fucking far away as possible.
Hmm.
Necessarily. Only under one condition will they be interested in coming closer. When I say bulky, it applies to lone pairs also. Only under one condition will they be interested in coming closer, which will be if they can do intramolecular hydrogen bonding.
Yes. Yeah. F and O. Yeah.
Now, to understand the intramolecular hydrogen bonding, you need to unfortunately see the structure of cyclohexane a little bit more closely. That unfortunately means I'll have to sit and make that structure now. Give me a couple of minutes.
Yeah.
Not a couple of minutes really. Another minute or so. So effectively, I have like 3 carbons down here. I'll add 3 more. So I'm just going to connect 6 carbons bluntly,
Yeah.
and you will be able to see what's happening there straight away. Basically, currently your visualization of chair form is not perfect.
Hmm.
So this is the actual chair form.
Uh,
You see it?
yes, sir.
Now I will show you how to position it. Watch how it is. Stupid split, that thing is crap. Okay. Hmm. Watch what's happening. Watch how it is positioned. Can you see there are 3 bonds on which it is sitting on the thing?
Yeah. Axial bond.
Exactly. And there are 3 bonds up here. So the axial idea here is these are the guys which are on the vertical axis.
Okay.
All right. Equator is going to be on the horizontal axis.
Everything other than those, pretty much.
Correct.
Huh.
So these guys are all going to be on the equatorial here. They're all going to be on this plane. Horizontal plane slightly up and down.
Yeah. Yes.
One pointing up, one pointing down. One pointing
Yes.
up,
Yes. Yes.
one pointing down. One pointing up, one pointing down. So that they have
Hmm.
enough space away from themselves. And there are three fellows on top and three fellows in the bottom.
Hmm.
So these three are in the same spatial region, roughly.
Yeah.
So if I have a fat group here, here, and here, they are problems.
Okay.
What are these locations? This is carbon 1 na. This is
Hmm.
2. This is 3. This is 4. This is 5. That means carbon 1, 3, and 5.
Hmm.
This guy was 1. This guy is 3. This guy is 5.
Yeah.
So carbons 1, 3, and 5 are the ones which are actually going to be in the same planar region if they are axials. Have a look again.
Okay.
Don't try to visualize too much. Our brains are not that capable of doing it. Someone as
Hmm.
intellectual as you is not going to be that sharp at visualizing. I'm guessing your Rubik's cube solving nonsense, you would have started solving better once you learned the solution.
Yeah.
And you would not have figured out the Rubik's cube by yourself.
No. Yeah.
So yeah. So you are not a visual fellow, you are an intellectual. So let's not go into that part there. So here you're going to be having this is one fellow here. These three are the ones which are going to be on this plane here, the axial fellows.
Yes. Yes.
Correct? The ones which I'm going to be pointing out with my hand here.
Yes.
Right? These three are going to be alternating carbons. This is
Hmm.
carbon 1 na, this is carbon number 3, and this guy is carbon number 5.
Hmm.
And their axials are the ones which are going to be in the same plane,
Yes.
the plane of this stage. That means their axials are the ones which are going to be having maximum repulsions.
Hmm.
So if I have FACSO groups on any of these three axials,
Yeah.
that's bad. They will have repulsions. How will they fix the repulsions? They will switch them into equatorial. Basically, let me put the groups and show you. That will be easiest actually.
Huh.
Let me put the groups there and you'll understand that more clearly.
Hmm.
Up is easier. I'll put it on up. Putting it up is easier. Basically, the same thing now.
Yes.
In up, you can see more clearly also.
Yeah.
So as you can see here, you're having three blues on top here, correct?
Hmm.
Now, the point here is this. The blue is not one fellow there. The blue can be imagined like this.
Hmm. Okay. Yeah.
Each of these is a fatso like this.
Hmm.
What happens then? If this fatso is having more fellows connected,
Yeah.
it becomes very fat.
Yes.
So if each of them is going to be, let me add one more fellow also onto this. If there are two groups attached like this,
Yeah.
on this one fellow here, and if there is going to be one more like this over here, each of these blue, what to say, circles, which you see is like this big fellow here. What will happen then? This guy also wants space. This
Yes.
fellow also wants space. This fellow also wants space.
Yeah.
There is not that much space available, literally.
Yeah.
So when you're not having enough space available, you will literally have crowding happening there. So this and this are now getting crowded by this fellow here.
Yeah.
And that is basically what is going to be a big problem when you are going to be having fat groups present in axial locations which are alternating. So these are alternating carbons, as you can see, right? So this
Hmm.
is carbon 1 now, this will be carbon 2, carbon 3, carbon 4 here, carbon 5 is this guy now. So the ones which are having groups are 1, 3, and 5.
Hmm.
Now, if these are in axials like this, they can change. How? They just flip. Now, I didn't do anything. I just flipped it around.
Yeah.
Just flip things around a little bit around. Now look
Yes.
at where they are. Now this is going in one direction, that is going in one direction, that is going in one direction. And
Yeah.
yeah. And as you can see, they are all now in equatorial.
Hmm.
They are in equatorial, they are all in some direction. So if I put one fat group here, let me show you by putting the fat fellow here. If I replace this with this guy, as you can see, it doesn't matter. It's going in one direction. This will go in one direction. This will go in one direction. So I can happily put fat groups now.
Hmm. Yes.
You're understanding the idea here? So when
Yes,
there
sir.
are fat groups present in alternating locations, what's the key learning from that? Never put fat groups in alternating position
Axial.
on axials. Why?
Hmm.
Because if you put them on axials, you're basically putting them in the same,
Increasing the repulsions.
which
Hmm.
means you're purposely increasing crowding. So when you can have a hydrogen bond possible in that case,
Then you can put.
then you put them.
Hmm.
So if I have, say, cis 1,3 dihydroxy,
Hmm.
write it down. Cis 1,3 dihydroxy system. What do I want? It's a dihydroxy, correct?
Yes, hydrogen bond is possible.
Exactly. That means I want the two OH groups as close as possible.
Hmm. So best to put them
So,
in axial position.
exactly.
Hmm. So, but then if you put them in, okay.
You want them as close as possible.
Would any other repulsions be greater than
Think,
like
think,
you?
think, think, think. Don't ask me the question. You think. I didn't give you anything else over here. Right? I just bluntly said cis 1,2 dihydroxy, 1,3 dihydroxy.
Hmm.
This is the best one. So axial would be better because I can have intramolecular hydrogen bonding being a possibility here. Now, if I had, say, 1,2 dihydroxy or 1,4 dihydroxy, what would I prefer in that case?
Then you would want to
If it
want
is
to be
cis,
the
if it is cis, what would I prefer?
cis. Okay, 1 second. Uh,
Let's go with 1,2 first. 1,4 is a little bit more complicated. 1,2 first.
hmm.
1,2, they are
One,
never going to be having intramolecular in this case,
correct.
right? So I don't need to give a
Different
shit.
planes. Yeah.
Hmm. So I'll go with, it doesn't matter.
Axial equatorial or equatorial axial.
Both are same. It doesn't make a
Hmm.
difference. It will
Hmm.
depend on the other groups which are present, how the others are going to be modeling themselves around this. Same way, if I'm going to be having 1,4
One
also, it's
four.
going to be similar, excepting with one issue there. In the boat conformation in 1,4,
Oh, then you can put axial there.
not just axial, you will have the fellows that are axial being pointed like this. The other fellows will be going like that. Axial fellows are pointed like this now, you can have
Oh,
hydrogen bond.
correct. Okay. So then what like what decides whether it's boat, half boat, or like sorry, half chair?
Stability, not
Okay,
for
sir.
individual pieces, but for the overall thing.
Okay, but then
Overall, total stability.
oh, okay. So suppose 1,4 dimethyl would have different structure than 1,4 dihydroxy.
Obviously,
Okay. Yeah.
because the 1,4 dihydroxy has a possibility of hydrogen bonding. The
Okay.
1,4 dimethyl has no chance of that. So 1,4 dimethyl will obviously prefer chat.
Yes, sir. Yeah.
And it will try to be in opposite angles completely, opposite directions completely.
Hmm. Yeah.
Whereas the 1,4 dihydroxy will prefer the boat. Under the case where it can have hydrogen bonding. If it cannot have hydrogen bonding, what will it prefer? Chair as well.
Hmm. Okay.